Clone graph. If you want to ace technical interviews at FONG and beyond, clone graph is a classic you must master. This pattern mastery 100 essential tests whether you truly understand recursion, graph traversal, and deep copying data structures. Did you know that a significant portion of candidates lose points here by shallow copying nodes, missing cycles, or failing to preserve graph structure? By getting this one right, you'll stand out in any interview and be ready for a whole family of graph problems. Here's the breakdown. You're given a node from a connected undirected graph, where each node contains a value and a list of neighbors. Your job? Return a deep clone of the graph, a new set of nodes, with the same structure and connections as the original, but no shared nodes. You can't just return the same nodes or rewire incorrectly. Cycles and shared neighbors make this tricky, so you need to carefully manage which nodes you've already cloned. Let's assess the challenges. Graphs can have cycles, so a naive recursive or iterative copy may loop forever. Nodes might be shared among neighbors. If you clone each node multiple times, the structure gets corrupted. We need a way to remember which nodes we've already cloned, so we can reuse the correct references. Use a hash map, dictionary, to track each original node and its corresponding clone. Traverse the graph, BFS or DFS. For each node, if it hasn't been cloned, make a new node and put it in the map. Then, recursively/iteratively clone all its neighbors. Here's our plan. Edge case. If the input node is none, return none. Create a map, old to new equals, to track original to clone nodes. Define a helper, DFS or BFS. If a node is already in the map, return its clone. Otherwise, clone the node, add it to the map, and recursively clone all neighbors. Return the clone for the input node. Let's try to implement it using solution 1. Time complexity is O(n) plus m. Space complexity is O(n). This solution uses DFS recursion to copy a graph. The tricky part about graphs is they can have cycles. That means you can come back to a node you have already visited. So the key strategy is to keep a map that links each original node to its cloned copy. When we first encounter a node, we create its clone and store it in the map right away. Then we recursively clone its neighbors and attach those cloned neighbors to the clone's neighbor list. If we ever see the same original node again, we do not clone it again. We reuse the existing copy from the map. That prevents infinite loops, and it guarantees every node is cloned exactly once. Before we start, we assume the graph uses a node structure like this. Each node has a value, and each node has a list of neighbor nodes it connects to. When we clone the graph, we create brand new node objects with the same values, and we rebuild the same neighbor relationships. But we do not point to the original nodes. First, we handle the simplest situation. If the input node does not exist, there is no graph to copy. So we return null immediately. Next, we create a map called cloned. This is the heart of the solution. It remembers which original nodes have already been copied. So we can safely handle cycles and shared neighbors without duplicating nodes. Now we define a DFS helper. The first thing it does is check the map. If this node was already cloned earlier, we immediately return the saved copy. This single check is what stops cycles from causing infinite recursion. If this node has not been cloned yet, we create a new node with the same value. Then we store it in the map right away. We store it before cloning neighbors. That is important because neighbors might point back to this node, and we want that lookup to work immediately. Next, we walk through the current node's neighbors. For each neighbor, we recursively get its cloned version. Then we push that cloned neighbor into the clone node's neighbors list. This builds the same connections as the original graph, but it uses cloned nodes. Once all neighbor links are attached, we return the cloned node. That returned clone becomes the neighbor reference for other nodes higher up in the recursion. Finally, we start the DFS from the given starting node, and the returned clone is the entry point to the fully copied graph. And that's how this algorithm works. It first checks for an empty graph and sets up a map to remember clone nodes, then it runs DFS to create each node once and recursively wire up clone neighbors while reusing clones from the map to handle cycles. Efficient, simple, and elegant. Test case check. Clone graph using DFS. Let's test our function using this input. 2, 4, 1, 3. 2, 4, 1, 3. These lists represent the neighbors of each node in the graph. For example, node 1 connects to nodes 2 and 4, node 2 connects to nodes 1 and 3, and so on. Here's why the solution works. We perform a DFS traversal of the graph. Whenever we encounter a node, we create a copy of it and store the mapping in a dictionary. Then we recursively clone each of its neighbors. If we revisit a node we've already cloned, we simply return the existing copy, preventing infinite loops in cyclic graphs. And that's exactly what our program outputs. 2, 4, 1, 3, 2, 4, 1, 3. It perfectly matches the expected clone structure, confirming that the graph has been duplicated accurately. Wrap up. So, our implementation is correct. The algorithm successfully creates a full deep copy of the graph using DFS and a hash map, efficient, accurate, and reliable. Let's try to implement it using solution 2. Time complexity is O(n) plus m. Space complexity is O(n). We are cloning a graph using BFS, which stands for breadth first search, with a map to keep track of what we have already copied. The key idea is simple. Every time we discover a node, we create its clone once. Then we store the original node and its clone together in a map. As we explore edges, meaning neighbors, we connect the clone nodes together in the same pattern as the original graph. This prevents infinite loops in cyclic graphs, and it avoids cloning the same node multiple times. Before we start, we assume the graph uses a node structure like this. Each node has a value, and each node has a list of neighbor nodes it connects to. When we clone the graph, we create brand new node objects with the same values, and we rebuild the same neighbor relationships. But we do not point to the original nodes. This function takes one starting node. It tries to copy the entire connected graph from that starting point. The first quick check is important. If the input is empty, there is nothing to clone. So we return null immediately. Now we set up our core tools. The map called cloned is our memory. It links each original node to its cloned copy. We start by cloning the first node right away. Then we prepare a BFS queue to explore the graph level by level. Instead of removing from the front of the queue, which can be slow, we use a head pointer. That head pointer moves forward through the array. This loop drives the exploration. As long as there are nodes waiting in the queue, we take the next one. That becomes the current node we are expanding. BFS ensures we eventually visit every reachable node from the starting point. This is the heart of the cloning process. For each neighbor of the current node, we first check if we have already cloned that neighbor. If we have not, we create its clone. We store it in the map. And we add the original neighbor to the queue so we can explore its neighbors later. Either way, we then connect the cloned current node to the cloned neighbor. We do that by pushing the cloned neighbor into the cloned current node's neighbors list. So we are doing two things at once. We make sure every node is cloned exactly once. And we recreate every connection in the cloned graph. Once BFS finishes, we have cloned every reachable node. And we have rebuilt all the neighbor links. The final answer is the clone of the starting node. From that node, you can access the entire cloned graph structure. And that's how this algorithm works. It first sets up a clone map and a BFS queue starting from the given node, then explores the graph while cloning nodes once and reconnecting their neighbor links in the copied graph. Efficient, simple, and elegant. Test case check. Clone graph using BFS. Let's test our function using this input. This represents a graph with just one node, and that node has no neighbors. In other words, it's a single isolated node with an empty adjacency list. Here's why the solution works. We start by cloning the initial node and placing it in a BFS queue. Then we process the queue level by level. For each node, we look at all its neighbors. If a neighbor hasn't been cloned yet, we create it and push it into the queue. Then we connect the cloned node to its cloned neighbors. And that's exactly what our program outputs. This confirms that the BFS cloning logic works correctly even for the smallest possible graph. Wrap up. So, our implementation is correct. The algorithm successfully clones the graph, even in minimal cases, using a clean BFS traversal and a mapping of original to cloned nodes. Efficient, accurate, and reliable. Clone graph. Let's do a recap. So, we just tackled one of the trickiest graph problems in interviews, clone graph. It's a true test of your understanding of recursion, traversal, and deep copying complex structures. Once you master this, you'll be ready for an entire class of graph and network-related problems that interviewers love to ask. Breakdown recap. At its core, this problem asks us to create a deep copy of a connected graph, meaning we build entirely new nodes that mirror the original connections perfectly. The catch? Graphs can contain cycles, so careless recursion can loop forever or duplicate nodes. Assess recap. We compared possible approaches. Brute force copying fails because of repeated nodes, while using recursion with memory tracking works beautifully. The key insight was to use a hash map to store already cloned nodes, so every original node maps to exactly one copy. This ensures no duplication and handles cycles cleanly. Structure recap. Our plan was simple yet powerful. Handle the base case when the graph is empty. Use DFS to explore and clone each node. Store each clone in the map, then recursively connect its neighbors. That's it. A clean, recursive structure that mirrors the graph one layer at a time. Implement recap. We implemented the DFS-based solution. ran it through LeetCode, and it executed flawlessly. No infinite loops, no shallow copies, and no structural mismatches. The cloned graph preserved every connection while remaining fully independent of the original. Check recap. After running multiple test cases, the cloned adjacency lists matched perfectly. All cycles, neighbor relationships, and node values aligned as expected. All test cases passed with optimal performance. Closing insight. The big takeaway? Clone graph is all about thinking recursively, breaking complex structures into smaller, familiar problems. Once you grasp how to track references and prevent duplication, you unlock the mindset needed for tackling any advanced graph or tree problem in technical interviews.